All right, class, let's see if I can do another video solution for you. Number 45 from chapter 28 here. Let me read it here. It says, a rechargeable battery has a constant EMF of 13.2 volts and has an internal resistance of 0.85 ohms. It is charged by a 14.7 volt power supply for a time of 1.8 hours. All right, so I guess it's looking something like this. We've got the charging battery, so I'll make the EMF. And this is 14.7 volts. Let's see, a rechargeable battery has a constant EMF and an internal resistance. It is charged by a power supply. Okay, so they don't really tell me an internal resistance to the charging battery, but the recharging battery looks something like this. It has an EMF of 13.2 and then an internal resistor of 0.85 ohms. All right, so what ends up happening is the current flows through here, and as it flows through, because of the resistance, some of that turns to heat. And then, of course, because of the EMF here, some of this is storing up a chemical reaction here. Of course, they're undoing it here. In fact, this has the numbers that would associate with a sulfuric acid and lead oxide battery. So this is like a car battery here. So we're charging this up with something that's a little bit higher in voltage here. Now, they do say constant EMF is charged with a power supply. Okay, yeah. So this is a typical number. If you have a voltmeter on your car, you'll see that the alternator has a constant voltage adjusted of about 14.7, 14.8, and it's used then to charge your car battery. So the numbers here are good numbers for a typical automobile. But anyways, we're going to charge this for 1 hour. And 1.8 hours. So if I say power is equal to the voltage times the current, and of course, remember, we've got to go back to Physics 121 from this, the definition of power is energy per time. So if we take power and multiply it by time, we're going to get energy. Okay, so if we know these three things, we can figure out how much energy goes into this battery. Now, let me keep reading the question. It says, after charging the battery, after charging the battery returns to its original state as it delivers a constant current to some load resistor for 7.3 hours. So maybe we charged it up, and then maybe we use this battery, and so maybe it's more like marine battery, and so maybe this battery is in our boat or in our RV or trailer or whatever, and so now we run the lights for 7.3 hours. It says find the efficiency of the battery as an energy storage device, and then they give us the definition of how to define that. It says this, the efficiency is defined as the energy delivered to the load during the discharge, then divided by the energy delivered by the power supply. So let me start there. How much energy is delivered by the power supply? So using this formula, how much energy is delivered from the power supply? Now, I know the voltage of the power supply, and I know the time. They said 1.8 hours. What they don't directly give me is the current. So I need to do a loop rule here, and there's just one loop to figure out how much current there is. And so starting at this point in the loop, I would say 14.7 volts up And then since it's charging, the current would go this way. So this would be current times the resistance of 0.85. So that'd be a minus. Then it would be going against the EMF, so minus 13.2, and we end up back where we started. So from that information, I can figure out how much current goes into or is coming out of this power supply as it is charging up this rechargeable battery. So I'm going to go ahead and take the 14.7 and subtract the 13.2. Imagine moving this to the other side. So then dividing by the 0.85. And so we're talking about a current of about 1.76 amps during the charging process. So to figure out how much energy then would be coming out of my power supply, I will take the voltage times the current and multiply it by time. So the voltage is the 14.7 volts. The current I just found is 1.76 amps. And maybe I should watch my units carefully here. Maybe I'll just do it right here. If this is a volt, so I got volt times an amp. Remember, a volt is a joule per coulomb, and remember, an amp is a coulomb per second. So this would leave me with joules per second, which is, of course, a watt. So these two multiplied together is a watt. So if I multiply it by time, I would want that time in seconds so that I'd be left with joules. So when they say 1.8 hours, I'm then going to multiply by 3,600 seconds in each hour. So hours would cancel, and then I'd have seconds, and the seconds with a watt then leaves me with units of a joule. Okay, so getting a number here, 14.7 times 1.76 times 1.8 times 3,600 comes out to be 1,067,650 joules of energy. So that's the energy, again, delivered by the power supply. Now, let me just make it very clear that right here you're going to see some loss in efficiency right away because some of that energy goes to heat. And some of it goes to the chemical reaction in the battery. And of course, you probably know this most often with, charging your cell phone, since you do that pretty fairly often, is once you plug it in, you'll feel it begin to get warm. And that's energy that is wasted. It's energy that's not going to charge up the battery. And so we already see a loss of energy. And it's not really part of the problem, but I am kind of curious. That loss of energy would be what? And so we could do the same thing, power multiplied by time. And maybe for this case, I squared R for power multiplied by time might be the way to figure out how much is lost there. We know it's 1.76 is the current. We'll square it. The resistance is 0.85, and the time is the 1.8 hours times 3,600 seconds. So just out of curiosity, again, I don't know if that's even worth our time to investigate, but I am kind of curious then how much we're losing into heat. And it looks like 17,062 joules are lost to heat. And so the difference between these two must be the amount that actually goes into storing the energy. But see, that's not the only place we're going to lose energy and therefore have an efficiency that is less than 100%. See, already we put in this much energy, but we've lost this much. So we're never going to get all that energy we put in out. We've already made some heat. But I think we also have to conclude that there's going to be some heat loss while this new charged battery is now discharged. And so getting the current out, it has to run through this resistor, and therefore it's going to get warm. And so, again, maybe you've noticed that about using your phone. So not only does it get warm while you're charging your phone, but it gets warm while you're using your phone. And so while you're using that phone, it can get pretty warm. In fact, when I make these videos, I go up here and I grab the phone. It's usually pretty warm because it's been on for, sometimes 30 minutes, or like when I do the solutions for the test, for 2 hours, and it's just really warm. And in the process of being warm, of course, there's a loss of energy here. So let's keep going with this. There's more energy loss to consider. So as I go on to page 2, let's keep reading here. It says, after charging, the battery returns to its original state as it delivers a constant current to a load resistor for 7.3 hours. Okay, so taking the battery that we just charged up, so 13.2 volts is the EMF, and it has an internal resistance of 0.85. And so I'll just kind of put a little dotted line around there. So there's my battery. We're going to use that battery and run something. And so, like I said, maybe this is a marine battery. So we charged it up, and now we're running the lights. Who knows? Or a motor for our little boat because we're running out there. Or maybe just a light. You go fishing all night long, and you leave this light on for 7.3 hours. Okay, and I'll just put a little R here because they don't tell us what the load is. So that makes it a little trickier figuring out what's going on here. But we do know this, then, that it says it returns back to its original state. So in other words, it loses all the energy that was given to it. And so, well, how much energy was that? Well, actually, that's maybe where this can be quite useful here, because then I can say here that the amount of current, energy, that is stored in here is the 167,650 joules minus the 17,062 joules. That's how much was in here. Let me grab a calculator for that. All right, so coming up here, I'm going to take that number and subtract this number. All right, so this has 150,589 joules that were, first of all, stored in it while it was charging, and now, second of all, is going to come out of it as it is discharging, okay, for this much time. All right, so this comes out of here and goes to both here and here. But what I can do with that number then is say that equals to the current times the voltage multiplied by the time. And then from that, I can figure out how much current is actually then coming out during this process of discharging for 7.3 hours. All right. So current is the unknown. The voltage is the 13.2 from that EMF. The time is the 7.3 hours, and don't forget the 3,600 seconds in 1 hour to make the units match. Okay, and then this has to equal the 150,589 joules. So this will let me figure out how much current is coming from this chemical reaction here. So taking the number and dividing it by 13.2, dividing that by 7.3, divide that by 3,600, and we get a 0.434 amps. So there is the answer to the currents as it is coming out or discharging. Now, again, kind of like we did while it was charging, we can kind of see then where does that energy go? Well, some of it goes to heat here, and some of it goes to this load resistor. Now, we could do this in a couple of ways, but I think since we know the resistance of the internal one, let's do that. We know that some of this 150,000 goes to heat here, and the rest of it goes here. So let's find out how much goes to heat here. So let me go I squared R for power and multiply by time. So this is the 0.343 amps that I'll square. The resistance of 0.85 ohms times a current of the time for the current, 7.3 hours times 3,600 seconds. So that's how much then of the energy goes to heat in the battery, warming it up, and then the other energy goes to whatever we're running. Okay, so I'm going to take that number and square it. And I will multiply it by 0.85. I will multiply that by 7.3, and I will multiply that by 3,600. And so this will be 4,210. Okay. Now, let me take that away from the 150,000. So here's the 150,000. Let me subtract how much was converted into heat, and then say that the power delivered or the energy delivered to my load during this 7.3 hours was 146,379 joules. So that's how much was actually then delivered. Okay, so now to finish the problem, let's get an efficiency by saying, okay, how much energy was actually delivered to the load, here it is, versus how much was actually put out or came out of the power supply into charging it. Remembering we lost a little bit while we were charging it, and we lost a little bit while we're discharging it. And what I lost is heat through that internal resistor. And so of the 167,650. And so I have 146,379 divided by 167,650. Oh, my bad. Comma, not a period there. And then hit enter. And we're looking about 87%, 87.3%. All right. Well, hope that helps, both in the sense of how do you do the physics of it, but then also in the practicality. That's what I kind of like about these two chapters is we're now getting into some application, some practicality, and seeing where do these actually apply. All right. Take care.